Welcome back friends for another edition of quantum field theory and quantum entanglement. So, we are continuing with the quantum electrodynamics. And we will proceed with it essentially, and in the last various cases essentially what we have seen is something called as spinor electrodynamics. So, what we have seen so far is called spinor electrodynamics, in which case what we actually studied was a spin half particle, which is essentially an electron interacting with a photon, which has electrodynamic interactions essentially, photon essentially. So, this is called a spin half particle interacting with a photon, which is called spinor electrodynamics. Now, people also put quantum electrodynamics and so on. So, now suppose if we have a situation, but there are particles which do not have spin also having electric charges, like for example, how about particles, spinless particles with electromagnetic interactions? Are there any such particles? Yes, of course. Are there any? Okay. So, what are such particles? Let us take pions. Pions come as pi plus and pi minus. These are fundamental composite particles. But it does not matter, essentially these are fundamental for the scale of physics we are doing. So, these are composite particles, pi plus and pi minus, and they are electrically charged. So, we have looked at detailed about this pion scalar pion field theory, which is nothing but the scalar field theory in great detail. Now, pions we said have electric charge, so they should interact electrodynamically. So, such a theory is called scalar electrodynamics. So, what is scalar electrodynamics? You have a pion, charged pion essentially, okay, interacting with photons. So, in general, but this need not be the only case, you have various scalar mesons, and these need not be fundamental particles also, okay. They could be other particles essentially, okay. So, easy description would be this. So, how do you write the scalar electrodynamics Lagrangian? So, the trick is the same. So, the trick what we have seen is that if you impose a U1 electrodynamics, so the coupling happens through A mu, okay, U1 electrodynamic theory, or U1 means we have seen that it is unitary group which is just e power I alpha of x q. So, if you have a U1 electrodynamic theory, the photons come as essentially as A mu, they have vectorial interactions. So, the photon fields is vectorial in nature. So, you need to construct a vector, okay, you need to construct a vector for the scalar fields, and that vector comes only from the available vector 4 vector is just del mu, or okay, it's or IEP. This is the only vector available essentially. You have only the momentum operator essentially which is available. So, with this vector you can write down the interaction with another vector field which is the A mu field essentially. That is the basic idea. So, you can write the Lagrangian, you start with, so with this idea, so what you do is you start with the original Klein-Gordon field, okay, phi dagger phi square minus 1 by 4 f mu, but to add to the interactions you change del mu to d mu. So, this gives me so this is the entire scalar QED Lagrangian. At the first shot it looks very similar to the ordinary QED Lagrangian, okay, it looks very similar. So, it looks very similar to the ordinary, but it has its own subtleties in the and we will find what these subtleties are once we expand the interaction terms. Okay, let us try to dig out the interaction terms and then we will see what are the subtleties involved. Okay. Good. So, what we have, so the interaction term is this. So, let me expand this. Now, what is del mu? Del mu is equal to del mu is equal to del mu plus IE A mu. This is what is called as minimal coupling. Okay. Now, you put it back into the Lagrangian, into this theory whole star now you see the initial terms, this has 4 kinds of terms. The standard Klein-Gordon type terms, kinetic terms. Now, then and then okay, E square A mu okay, phi star phi, okay. Then there are the cross terms. So, this is coming is second, okay. This is coming in second in the coupling constant, second order in coupling constant, this term. Okay. Then there are the cross terms which are essentially the other term would be Okay, these are the two cross terms which lead to the interactions essentially. So, you have three terms, these two you see that they are conjugates of each other. This is phi star phi, this is another interaction term. So, these two terms which are interlined essentially can be combined, essentially then can be combined into a single vertex essentially. So, since we have looked at the Feynman rules of the scalar field theory very well, okay, I will just focus right now on the interaction terms. Let us write down the interaction terms. So, this either you take the momentum of the phi star or you take the momentum of phi. So, you see that this has the vertex of this, let us write down the vertex. So, this will be I E. So, let me put it as P, P1 or P and the P prime, say for example. Okay. So, this will take P mu minus P mu prime. Okay. These both terms lead to the Feynman rule. Okay. Both these terms which are now, let me put them in red, both these terms give you the Feynman rule, okay, I E P mu prime. So, this is shocking, this is momentum dependent completely shocking for us, because we have not dealt with an interaction term which is momentum dependent. Okay. So far. So, but the first interaction term which we are the simplest first interaction, which we removed the spin of the spinor electrodynamics and made it into a spinless particle electron essentially, or just a scalar particle. This gives me momentum dependent couplings for the gauge couplings essentially. Now, you have to consider what is the thing I E A mu gamma mu for spinor electrodynamics. Okay, good. So, now then this is like whether you want to, this is almost like the QED Lagrangian, except that in the QED Lagrangian you have a constant coupling constant, whereas here the coupling constant is momentum dependent coupling constant. Now, there is another diagram sometime, okay, another diagram which is also very important, comes from the yellow term or cyan term. Okay, this may not be cyan, it may be called turquoise or something. This is this coupling. And this coupling is 2 photons and 2 pions. Okay. Now, you see that this coupling has a strength I E square, there is no I, sorry, it has a strength which is E square. Okay. You remember it is a real coupling. So, where is this coupling which we have written here, this is the blue thing, okay. So, photon field phi star phi. So, this has a coupling which is E square, which is also sometimes called Seagull diagram, just from the geometry of this thing. So, this is also called the Seagull coupling. and which, because it leads to Seagull diagrams, essentially Seagull coupling. Okay, and yeah, so this is a new thing, and this will also play a role in some process in scalar electrodynamics. Now, normally when you do um, meaning spinor electrodynamics and scalar electrodynamics, the difference is not much. Okay, the difference is just the spin factor essentially most of the time. Okay, even though there is a moment independent coupling and so on, so and everything, things are reasonably under control, and you end up having almost the same results for both say for example scalar electrodynamics and and quantum spinor electrodynamics. But there are some process in which this diagram, the Seagull diagram with the Seagull coupling will play a role essentially. Okay. So, let us do the same things as what we have done earlier. So, let us start with molar scattering. Scalar QED. Okay. So, molar scattering would be what? Phi phi going into phi phi, or phi star going into phi star phi star. So, it has the same diagrams as earlier. So, phi 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 phi. And now remember, phi star is like positron, phi is like the electron. Now, you can compute the amplitude. Okay. In this case, it will come out to be, for the molar scattering, it will come out to be something like m mod square is equal to e power 4 s square plus t square plus u square whole square by t square u square. Now, compare it, because the difference I am telling you, that there is also the cross diagram plus cross diagram. Time is in this direction. This is for the scalar QED. Now, if you compare it with ordinary QED, this is equivalent to the massless limit, say for example 2 e power 4 by t square u square s power 4 plus t power 4 plus u power 4. You see the difference. The numerator, first of all, there is a factor 2. Okay, there is a factor 2 here, and secondly, the numerator goes as s power 4, t power 4, u power 4, whereas this goes as s square plus t square plus u square whole square. So, there is clearly something to study in more detail. Okay, and it has some interesting features essentially, is that so they are except for the spin factor, the numerator is almost the same. So, they look almost the same. Okay. Okay, they look almost the same, because s power 4, t power 4, u power 4 and order of magnitude, except for a 2 factor, and then there are those cross terms which will make a difference essentially. So, these extra factors which you have essentially are removed by the you get, when you take the whole square, you have s square t square u square t square. These are the things which are not allowed by the spinor things essentially, and so that is why they remove them essentially. So, in spinor you directly have S power 4, T power 4 and U power 4. Okay. Now, let us move to the second one, which is essentially is Baba scattering. So, the diagrams are the same. So, in this case too you have m square scalar and m square spinor Okay. Now, you see there is again a factor 2 in the Baba scattering, a factor 2 sitting here. Okay, let me just so this is just a factor 2 sitting here, and then the numerator is different, which are the cross terms which we said are removed essentially. Other than S and T combinations, everything looks essentially the same. It has the same structure for the Baba and molar scattering. The differences will start coming in process like Compton scattering. So, in Compton scattering we have seen major differences will start coming in process like Compton scattering. So, Compton scattering is what? E gamma, E gamma. So, what we did was we had these two diagrams which okay, E gamma, E gamma. And then the other one was with the cross essentially. So, we had the Compton scattering, okay. We had S channel also is there. Yes, and then there is the T channel essentially. So, you have okay. So, we had the S channel and U channel, okay. And then now this is what we had in E gamma, E gamma. Now, you have say pion gamma, pion gamma. So, you have phi gamma, phi gamma. So, you have same diagrams. In addition to these diagrams, you also have so there is a third diagram which is roughly constant essentially. These two are momentum dependent in principle. Coupling constants, and at the end of the day you have m square scalar QED is equal to 4 e power 4 isotropic. It is a constant essentially. It just becomes a complete constant. So, this new diagram plays a role plays a role in Compton scattering, it plays a very important role in Compton scattering, okay, whereas in the scalar Q, in the ordinary QED, okay, in ordinary QED what happens is this has a rich polarization structure. So, you can study the polarization of the electrons in Compton scattering. So, you can study the polarization of the photons if left handed electrons, right handed electrons, a photon which is polarized L or whatever essentially, and you can study this. It has a very good polarization structure, whereas you do not have any polarization structure in scalar electrodynamics in Compton scattering. If you do with the scalars, the entire spin, the polarization, the spin, all that information is completely lost, and what happens is these two diagrams, the main parts of these two diagrams cancel each other, and what you have is only this third diagram which will contribute, okay, which will contribute, and this will lead you a completely isotropic, meaning the contribution is independent of it is same from every direction essentially. So, it does not have any angular dependence, okay. So, no angular dependence in this case, okay. If you take a differential distribution, so it just gives you a constant number essentially, okay. So, no angular dependence, so which is interesting on its own essentially. Now, the other places, other two places before we close the thing essentially, where the scalar thing is different is the case of say for example pair annihilation. So, we saw the diagrams for the pair annihilation. Essentially you have in the QED, okay, let me draw in QED. So, pair annihilation in QED is this, okay, and in scalar QED instead you have plus you also have the Seagull diagram or the other diagram in which you have this diagram essentially. So, this here also this will play a role essentially, and so this will also play, give you a role will be something like, you know, if you have mass term essentially 1 by T, okay, y is equal to, so something like y is equal to m square 1 by T minus m square plus 1 by u minus m square. There are two diagrams, and then the summing over all the polarization, all the diagrams in the scalar case, okay, you end up having something like this essentially 8 e power 4 1 plus y square plus y square. Some such formula essentially, whereas in the pair creation you end up having for the in the QED case, this has a form which we saw already, something like T by U plus U by T. So, again pair annihilation and pair creation are pair annihilation and Compton effect are related by crossing symmetry. Now, you can match them both essentially, but you see the difference between the scalar and the QED case, which is quite different essentially, which is quite different, okay. Again the scalar case is always in the massless limit. You can take the massless limit, okay. In the massless limit is just 8 e power 4 isotropic. So, it will be 4 pi whatever it is essentially. So, this is nothing but 8 e power 4 because everything gets cancelled in the massless limit, okay. Whereas, this is the massless limit for this one. As you said, if we keep the mass, the formula is much more complicated essentially. So, in the scalar case the massive limits are easier, essentially the massive formulas are much easier. So, as we have seen that pair annihilation, pair Compton scattering, and the third pair creation was the same story. Pair creation it's the same thing, essentially you have photons coming in, same story essentially. So, you have the two diagrams in scalar QED. So, same story essentially as in, so this is his E is just 2 e power 4, okay. Whereas, QED T by u plus u by t. So, what is surprising is that in the scalar QED when you expect large momentum dependence and so on, so because of the presence of this the coupling constants which are momentum dependent, instead you end up having with actually no structure at all, in the sense in the phase space you do not have any structure at all, it is completely isotropic, and you end up having constant cross sections, okay, in the scalar QED, whereas ordinary QED has extremely rich structure essentially, okay. So, what I tried to show you today is that changing the spin and studying the electrodynamics has very interesting features, essentially the scalar electrodynamics has very interesting features, and we will you will see that especially while for in some process the difference is just the spin spin counting, essentially it is a factor of 2 and so on. So, whereas in other process essentially like Compton scattering, pair creation, pair annihilation, the third diagram which is the Seagull diagram will start playing a role, and then you end up having only constant cross sections essentially, okay. So, I should also add this thing here, essentially pair creation. So, you end up having constant cross sections, and this is the interesting part of the scalar QED. So, okay, now from the next lecture onwards we will start moving for higher order corrections, essentially we will start looking at one loop corrections in QED. I will go in a very systematic and algorithmic way, and because we will try to do as much as possible for the one loop corrections, and then we will move to the second part of the lectures, which is essentially trying to study quantum entanglement, okay. So, the next few lectures will be on radiative corrections in QED, and once we are done we will move to quantum entanglement, okay. Thank you very much, I will see you soon.